Okay, so so this is where we left off last time. Last time we talked about causal graphs and causal DAGs, the directed acyclic graphs, and um, how a causal DAG implies a probability distribution over all the variables. And we talked about the three types of paths with three nodes. We talked about the fork, the chain, and today we're going to continue our discussion about the third type, which is the inverted fork. So just to remind people the main stuff we went through last time. So for the fork structure, we have this kind of conditional independence. A independent of B, conditional on C. We went through some examples, and then for chain, we also have a independence result. A independent of B, conditional on the middle variable C. And we went through the proofs and the results examples for that. So now we're going to visit the third type of three node path. So this is called an inverted fork. So we have A and B on the outside. Both of them have arrows pointing to the middle node C. So in this case, this node C is called a collider because the nodes, the arrows collide on node C. So this is a very important and special case. So I want you all to remember what's going on. So, and in particular for this type of structure, we have this independence result. So in the above, we have A independent of B. It's not a conditional independence, but it's a marginal independence. So let's see how do we prove that. Then we'll go through some examples and discussions. Okay, so again, using the rule of products decomposition, we take in this as in kind of an axiom or an assumption for all the causal DAGs. So we have A, B, and C, the joint distribution equal to, we're starting from a root. So here we have two roots. We have an A and a B, both are roots. So we have P of N times P of B. Then the third one is P of C, conditional on the parents of C. So the parents of C here is A and B. So we have this relationship. And therefore, we can marginalizing over C on both sides, right? We integrating over C, so you can write integral in dc. So the left-hand side becomes the distribution of A and B, and the right-hand side, this part integrates to 1, and what's left is these two, so PA times PB. And therefore, this is the definition of A independent of B. So we have shown that in this inverted fork or in this collider structure, we have the two nodes on the outside independent of each other marginally. So this case, I said this is very important because it can be counterintuitive when you first look at it. And in particular, A is independent of B marginally, but if we conditional on C, usually this conditioning induces association between B and C. Sorry, between A and B. So we'll see an example on the next slide, but let me just comment on the terminology. So the fact that in the collider structure, the parents A and B are correlated when conditioning on the collider C. This is sometimes called association induced by conditioning on a common effect. And this is because C can be seen as the common effect of A and B. So we have proved A independent of B by math. Now let's look at why it is the case that when conditional on C, we have this induced correlation or induced dependence. Okay, so let's look at this example. So suppose we have two switches controlling a single light bulb. And suppose the light is on if at least one of the switches is on. So you can think of this as an OR operator, right? The light is on if switch 1 or switch 2 is on. Now, suppose the two switches are independent from each other. So you can think of them as each determined by an independent coin flip with probability 0.5, let's say. Okay, so this is our assumption. So this is how the problem is set up. Of course, we have the two switches marginally independent of each other. Now let's see, what if we conditional on the status of the light bulb? So if we know, for example, if we know the light bulb is on, that's the meaning of conditional on light bulb equal to on, then these two switches are no longer independent. Because if one of them is off, then the other switch must be on. Because we know the light bulb is on, we are conditioning on the fact the light bulb is on. In that conditional world, the two switches are no longer independent. So this is an example where when you're conditioning on a collider, the two parents who were independent are no longer conditionally independent. So last time we've talked about how these arrows can be interpreted as information flow. So if we try to think from the information flow perspective, then maybe you can think of things this way. Although I admit that it's not at all intuitive. So if you don't find it intuitive, you may want to just memorize the conclusion. But if we think from the information flow perspective, we have information flowing from switch 1 to the light bulb, from switch 2 to the light bulb. But if we don't do anything, we don't do any conditioning, then these are just informations flowing out of switch 1 and out of switch 2. So there is no exchange of information between these two. So they don't share information, and therefore they are marginally independent. But when we're conditioning on this light bulb, we are, you can think of this as the information flow from one of the switches. When we're fixing the light bulb, the information from one of the switches gives a constraint on what the information from the other parent is, because we require this to be fixed when we're doing the conditioning. And therefore, the conditioning induces correlation between the two. So this is an attempt to make an intuitive argument. But I think this example, at least, is very concrete and straightforward. Any questions? Okay, so now a generalized version is that, for example, let's look at this graph. So we have A and B collide on C, and C has a descendant D. So it turns out that if we condition null on a descendant of C, in this case, suppose we conditional on D, then this would also induce the association between A and B. So even though we're not conditioned on C, if we're conditioning on a descendant of C, we also induce correlation between the two. Why that is the case, let's again look at this example. We have switch 1 and switch 2. They all contribute to this light bulb, as we've seen before. So what would be a descendant of the light bulb? Let's see. So one example would be the brightness of the ground. If the light bulb is on, the ground would be lit up. If the light bulb is off, the ground would be dark. So now this is a one-to-one correspondence between the two, but you can also think of something as, you can add some noise to this brightness of the ground. Maybe you have another independent light with 0.5 probability to be on, 0.5 probability to be off, etc. But just to make things clear, I'm using this very simple example. So in this case, if we conditioning on this descendant of the collider, if we know, for example, the ground is bright, then we have information about the collider. Here is a deterministic information, but usually we have some probabilistic information about the collider. And therefore, we're still having information about the collider, which again induces correlation between the two parents. So this is the special case that can be unintuitive. The special case that when you don't condition on the collider, the parents are independent, but when you're conditioning on that, the parents are no longer independent. Any questions?
If we condition on the light, I guess C or the light
Yeah,
bulb, then D is independent of A and B.
correct. And that is
Yeah,
because that, when you look at one of the switches, switch, light bulb, and the descendant, that's a, what's it called? Chain structure.
yeah,
So that's why what you said is correct.
cool. Thanks.
Okay, great. So something get wrong with my LaTeX. Okay, so this is what we've seen so far. We have seen three types of paths: a fork, a chain, and an inverse fork. In the fork and the chain, when we condition on the middle, we have conditional independence. In the inverse fork, when we don't conditional on the middle, we have independence. But when we condition on the middle, we no longer have independence. So now I'm going to introduce some additional notation. So we're going to see this notion of blocking a path. This is essentially what we've seen before, but just a new notation or new terminology. So one terminology people often use is the notion of blocking a path. So this is an example. Again, in this fork structure, because we have this conditional independence, people say that C blocks the path from A to B. So, again, if you think about arrows as information flow, then it's very intuitive, right? This variable blocks the information flow between A and B. Another example, in the chain example, we have this conditional independence. So we say C blocks the path from A to B. And again, this is even more intuitive. This blocks the flow of information. And in the inverse fork example, because we have this marginal independence, so this is a quite different and very weird saying. We say that the empty set blocks the path from A to B, because the marginal independence is equivalent to independence conditional on an empty set. Now, however, because we have seen that when we conditional on C, these two are no longer independent, so using the blocking terminology, C does not block the path from A to B. Or sometimes people actually say, when we conditional on C, we opens the path from A to B, which were originally closed when we don't condition on everything, or originally blocked, I'd say. Okay, so yeah, sometimes it's kind of counterintuitive. So I guess the advice I'd like to give is to memorize the example of two switches and one light bulb. Okay, so now that we talked about the three node paths and the notion of blocking a path, essentially that's equivalent to independence consequences. Now let's generalize from the three node paths. We want to understand the big picture goal is that we want to understand when we see a causal DAG, what variables are independent from each other or conditionally independent from each other. Because ultimately we want to look at ignorability or conditional ignorability, right? So understanding the independence between variables is kind of the preliminary thing we need to do. So usually we have contain multiple paths in the causal DAG. So do we have a general rule for such independence or conditional independence results? And the answer is yes. This is called D-separation, where D stands for directional. So let's first look at the definition of D-separation and blocking a path. So we have seen blocking a path for these three simple examples, but in general, a path P is blocked by a set of variables Z if and only if at least one of the two satisfies. So if both are satisfied, that's fine too. Okay, so the first condition is if P contains a chain or a fork such that the middle node is in Z. In other words, if the path contains a chain and we are conditional on the middle of the chain or the middle of the fork, then we say we have blocked the path. The second condition is that P contains a collider, here B is the collider, such that the collider B is not in Z. In other words, we are not conditioning on the collider inside the path. And no descendants of B is in Z. So we are also not conditioning on any descendant of the collider with respect to this path. So when either one or two is satisfied, then we say that this path is blocked by this node set of variables Z. Right now, this may look a little bit complicated, but at least we have seen blocking for 3 special examples. So hopefully it's not too difficult to generalize to these situations. And we'll see specific examples shortly. But just one more definition. So let's consider a path, not a path, but 2 variables, x and y, in a graph. There might be multiple paths, right? Directed or undirected paths between x and y. Undirected meaning that it's not all the arrows are pointing to the same direction, but still every edge is directed edge. So consider 2 nodes. If we have a set of variables z that blocks every path between the 2 nodes, then we say that x and y are deseparated, conditional on z. Okay, so what's the use of deseparation as you probably would have imagined? If x and y are deseparated by z, if x and y are here and z is in the middle, it blocks every path, then we have this result. Then x and y is independent of z. X independent of y, conditional on z. So if we're blocking the path between x and y using the set z, then it gives this conditional independence result. So the proof is in, if you look at the course notes I uploaded online, you will see the references. Here somehow I'm messing up the LaTeX. This proof is given in a very early paper in 1988. So what this tells us is that now we have a procedure to determine conditional independence relationships for any set of variables and any set of conditionals, right? You give me 2 variables, you give me a set of z, I can tell you whether they are deseparated, whether the deseparation holds here for this conditional set. If it holds, we have conditional independence. If it does not hold, we don't know. But if it does not hold, then it's possible that there are dependence. So the reason I'm saying the last part of my sentence is because there is a converse version of the result, that if you have conditional independence, then you almost always have deseparation. But because this involves some additional technical details about, for example, what you almost have, what does it mean? So since we're not talking about these nuances, I'm not presenting the result. But please know this result at least. This is very useful and important. Okay, so now we're going to see some examples. I will, this is what I will do. I will go through the first 4. Oh, where's number 5? Weird. I'll go through the first 4, and then I'll ask you to spend some time to work on your own 6, 7, 8, 9. Okay, so let's see. So in the first 4, we're interested in. Let me use my pen over here. In the first 4, we're interested in the variable w and the variable t. Okay, so in order to determine whether they are deseparated, we first need to find out all the paths between these two nodes. Okay, so what are the paths? We have this as one path. I'll try to use a different color for each path. We have this as another path. We have this as a third path. So we have the 3 paths from W to T. Okay, so now let's see. So the first question is W and T deseparated by Y? So if it is, then we would need Y to block every path between W and T. And obviously here we see that this path is not blocked by Y, right? This is a chain. In order to block it, we need the middle part to be included in the conditions. It's not, so it's not blocked by Y. And therefore, the answer is no. What have I done? Let me just draw these back. Okay, so the second question is W and T deseparated by Z. Is it deseparated by Z? Let's take a look. So we have 3 paths, and we're conditioning on Z. So this is a chain, so Z blocks this blue path. Now, for the red path, what do we have? For the red path, we have, this is a fork, and this is a collider. So in order to block this path, this entire path, we need to either conditional on Y, because we're blocking this fork, or we need to not conditional on Z, because here we have a collider, and not conditioning on the collider blocks the path. And therefore, when we are conditioning on Z, because this is what we're asking in question 2, when we're conditioning on Z, we're opening the path from W, this red path. Are you following? Okay. Interrupt me if you have any questions. And therefore, the answer to question number 2 is, again, no. Okay, so let me clear things up. Pen. Okay, let's look at question number 3. Question number 3 is W and T deseparated by Y and Z? So we are conditioning on these 2 variables. Okay, so is it true? Does the deseparation hold? So first, we have seen last time that the blue path is deseparated by Z. So we have the blue path blocked. Good. Okay, now the red path. So for the red path, we have just seen that if we only conditional on Z, it's not good enough. But using the definition of deseparation or blocking a path, right? Because we have this fork structure in this red path, and we're conditioning on the origin of the fork, here variable y. And therefore, we are blocking the path because we're conditioning on y. And it's okay if we're also conditioning on z, because the definition of deseparation is that as long as one or two hold, the path is blocked. So here we're satisfying one, and therefore the red path here is blocked. Now for the other one is very simple. For the yellow one, because we have this chain structure from x to y, from y to t, and therefore when we're conditioning on y, we're blocking this yellow path. So the answer to question 3 is yes. Okay, so now for the fourth one, maybe we don't have to draw all the paths. Let's see. So are they deseparated when conditioning on x and z? So again, there is a path that we have seen that when you're only conditioning on z, it's not blocked because z is a collider. We're also conditioning on x, but x has nothing to do with this particular path. And therefore, the answer to the fourth question is no. Any questions so far? If there are
So in
no
general,
questions,
like
yes.
paths are invariant to direction, right? Like you just pick any edges that connect things regardless of the direction. And that's
Yes,
a path.
when talking about a path, it does not matter. Yeah.
But then it does, direction then matters when we're talking about forks and colliders.
Correct. Correct. Yeah. And there's also this other notion of a directed path.
Right.
When we use that term, it means all the arrows are pointing to the same direction. But in general, path can have mixed directions of arrows.
Okay.
Okay, so if there are no more questions, I'll give you a couple minutes to work on 6, 7, 8, 9. Then we'll see.
The answer for 3 was yes, right?
We'll
think I missed
shortly
it.
go through that. Yeah, I don't want to
No,
spoil
no, no,
it for
no,
others.
no, no.
Oh, for 3, sorry.
Yeah.
Let me see. Yes.
Okay, thanks.
Sorry, I have a quick question about the previous four
Yes.
questions.
Yes.
So when we were thinking about a path between W and T, did we consider the path from W to X to Y to Z to T?
Oh, that's a good question. Yes, I missed that actually.
Okay.
Yeah,
All
I
right.
missed that. That what we should have also considered that. Yes.
Okay, gotcha.
That's my mistake.
But probably it doesn't matter because every subpath has been considered before.
Maybe. I don't know the answer, but that's a good
Okay.
observation. Yeah.
All right.
Thank you. Okay. I'm sorry that I'll have to ask you to stop your work for the moment. I realize that this probably is my bad planning. That if you're first time seeing this, maybe it takes a while to work out these problems. So if you haven't finished, that's okay too. But the important thing, I guess, is that we want to use these notation in a particular blocking paths in what we're going to see next. So let's go through the exercises 6, 7, 8, 9 briefly. If you haven't decided on yes or no to a particular question, that's fine too. So what I plan to do now is that, so are you able to click like faster or slower in term on Zoom? Okay, good. So great, thank you. So what I'm going to do is that let's first discuss question number 6. If you think the answer is yes, you click slower. If you think the answer is no, you click faster. If you don't want to answer or haven't finished, that's fine. You just don't answer. Okay, good. Thank you. So it seems that we have reached a consensus for the among the responses, but good one. So, and the reason why it's not, the answer is no. The reason why it's not is because we have this path not being blocked. Okay, so now let's
Sorry,
look
I
at.
didn't know how to click the button, so that was my bad.
Oh, yeah, and that's okay. Don't worry. Yeah, if you can't click the button, you can write on the board and then erase it afterwards. That's fine too. So let's look at question number 7. Again, using the same buttons. Okay, thank you. So here we have some kind of disagreement between the answers. So I will try to explain a little bit. Okay, so let's see. The path between W and Y, there are a few. We have this one. We have one over here. We also have another one over here. Okay, and the question is, if we conditional on X, are W and Y deseparated? Are all the paths blocked? So let's look at it one by one. So first of all, of course, this path, this blue one, is blocked because it's a fork and we're conditioning on the middle. So for the other two, it's trickier. And let's see. So for the red path, we have a collider structure where Z here is the collider. So, I'm sorry. So when Z is not included in the conditional set, this red path is blocked. Remember, collider has the reverse conditional independence result from the other paths. Okay, so now we have this yellow path. For this yellow path, again, we have a collider structure, not on Z, but on T. We have an arrow pointing over to here. We have an arrow pointing to here. So again, because T is not in the conditional set, this path, this yellow path, is blocked. Now, it doesn't have to be a direct collider between Y and W directly. You can have a longer path, but resulting in a collider. If that happens, then this path is blocked as long as you conditional on the collider. So to see it clearly, we have, going back to the definition of blocking a path, if the path contains a collider, not necessarily A and C have to be the ends of this path. As long as there is a collider inside the path, then we're okay. We will have independence. So therefore, the answer to question number 7 is yes. Okay, so for the sake of time, I'm not going over 8 and 9, but I'll think about a way to resolve it afterwards. I will. So remember your answer, and I will post the answer to 8 and 9 on the discussion forum afterwards. Okay, now we're going to switch to our new lecture slides. Do you have any questions in the meantime? And I remember when I was first studying this deseparation things in a completely different course, in a computer science course on graphical models. At that time, I didn't know causal inference, but it was quite confusing to me. So if you find these kind of things confusing at first, that's totally normal. But hopefully, as you try to grapple with the concept, you will get more and more familiar to that. Okay, if no more questions, now we can go to the exciting part. Previously, we have been trying to lay the foundation, the mathematical work for causal DAGs. We have talked about what is a graph, a causal DAG, and the rule of product decomposition. We talked about these 3 types of structures, and their implied independence results. And we just talked about what is a D-separation and the resulting conditional independence. So now let's always remember our ultimate goal. Our ultimate goal is that if we're given a DAG, such as the one in the following or a more complicated one, we want to find variables that we can include in X so that conditional ignorability hold. Okay, so right now it's not clear what that, how do we find such an X? Because here we have potential outcomes, and everything that we have seen so far have no parentheses 0, parentheses 1 yet, right? Everything we have seen are kind of observed or variables in the real world, not in a potential world. So, but in any case, this is what we want to do. So, is there a way to do this? The answer is yes, and there are multiple ways to do this. One will mainly focus on one of such ways, or a criterion, and this is called the backdoor criterion. So we'll see what it is. And in order to introduce the criterion, we'll first know what is a backdoor path, right? This is called a backdoor criterion. And we'll also look at front door paths, because these are also important concepts in terms of causal DAGs. Okay, so some notations. We have A as our treatment assignment. Oh, by the way, so up to now, we haven't been paying attention to which variable is treatment, which variable is outcome, which variable is covert. We're just throwing a random English letters and we play around with the graph. Now we will distinguish between these variables. So A is treatment, Y is observed outcome, and of course, we want to understand the causal effect between A and Y, or the causal effect of A on Y. And we'll use other variables or other letters to denote other variables. What are other variables? Some of them could be pre-treatment covariates. Sometimes some of the variables are post-treatment variables, so measured as maybe a mediator between the treatment and the outcome, or some further outcome after the outcome is measured. And we'll see what these are, but they will be evident from each DAG. And also, some variables can be measured and some variables can be unmeasured. So far, we haven't been talking about measured or unmeasured variables, right? We're given a causal DAG with all these variables. We haven't been talking about, it really doesn't make sense, or it doesn't matter whether some of them are measured or unmeasured, because all we're talking about is conditional independence. Right? If the variables are unmeasured, then too bad. Even though we know the conditional independence, we can't use it. But so far, it doesn't matter for the purpose of our discussion. So this is what I'm trying to say. Right? Okay. So what we're trying to find out is what variables to condition it on to have conditional ignorability. We're not looking for what observed variables to conditional on to have conditional ignorability. So if we find out that the variables we need include unobserved ones, if I tell you, oh, I need to include like W and L to get conditional ignorability, and you tell me, oh, but L is unobserved, then okay, so we have this unmeasured confounding, and we'll see what do we do with that. But all my blah 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 is trying to say it doesn't matter for the sake of our current discussion, measured or unmeasured. Okay, so here you will see a lot of intuitive arguments, and I would encourage you to try to understand the intuition as I try to explain these arguments. And another reason is because causal DAG is useful in conveying intuitive causal assumptions, and especially if you're communicating with collaborators. So please ask questions if you don't understand or if you disagree with something. And also, these intuitive arguments, they can all be made rigorous using the language of structural causal models. If you're interested, these are the references. And finally, when I put something as a result in the text block, these are actually rigorous, mathematically valid statements, and I'll provide citations for the proofs. Okay, so now we're ready to discuss front door, backdoor paths, and the criteria that we're interested in, the backdoor criteria that tells us when do we have conditional ignorability. Okay, so a front door path from A to Y, treatment to the outcome, is a directed path that begins with an arrow coming out of A. So this is a very simple idea. These are two examples. If we have this DAG, this direct arrow from A to Y, this is a front door path. Front door, you will see why this is called front door when you see the backdoor path meaning. So this is another example. We have A arrow to Z, arrow to Y. So this one is a front door path, the highlighted one, because this is a directed path where each arrow has the same direction and it's coming out of A to Y. Okay, so what's the role of front door paths in causal DAGs? What information does it convey? In a nutshell, front door paths capture effects of the treatment, the causal effects that we actually care about. So, for example, in here, this front door path tells us that A directly affects Y. And we haven't talked about magnitudes of these arrows or quantitatively measure them yet, but you can intuitively think the more influential this arrow is, the larger effect we have. We won't get to actually doing that kind of analysis because we're not doing structural causal models or do calculus. If you read Julia Pearl's papers, you will see a lot of these. But here I'm mainly trying to give you some intuition. Okay, so another example where front door path captures the effect of treatment is here. So we have A to Z to Y. So you can think, oh, the treatment A affects the outcome Y indirectly through its effect on Z. Right? A causally affects Z and Z causally affects Y. So indirectly, A causally affects Y. Okay. So one important thing about front door paths is that because it captures the causal effect we care about, we do not want to block it in our analysis or in considering conditional ignorability. And in particular, so for example, if we're interested in this causal DAG, the effect of A to Y, we should not control for Z, or we should not conditional on Z. We should not block this path. And the reason is that because we care about if we manipulate A, how is Y affected? That's our causal, the notion of a causal relationship. So if we conditional on Z by holding Z fixed, then we would be controlling for an effect of treatment. And that's something we don't want to do. Why? Consider an extreme case. Suppose we have this very simple causal DAG. So remove everything about the L and the two arrows. Suppose we have A to Z to Y. In this simple DAG, we know from the previous lecture that if we conditional on Z, or if we control for Z, that's the same thing, that would make A and Y independent. Now, making A and Y independent in this DAG is obviously not something we want to do, because if they're independent, where's the causal effect? Right? So we don't want to do this. Okay, so the key lesson for the front door paths is that to assess causal effects, we don't want to control for variables in the front door path from A to Y. Any questions for the front door paths? Okay, so now let's look at backdoor paths. These are, I'd say, the more important concepts in causal inference, at least for causal DAGs. So what is a backdoor path? The backdoor path is also from A to Y, and this is a path that begins with an arrow going into A. So remember, front door path starts with an arrow going out of A, and the backdoor path starts with an arrow going into A. So these are two examples. Here, this path highlighted from A to L to Y is a backdoor path because it starts with this arrow. And here, from A to L to W to Y, starting with an arrow pointing into A, that is a backdoor path as well. So what's the role of backdoor paths in causal DAGs? Backdoor paths confound the causal relationship between A and Y. In other words, backdoor paths induces spurious correlation between A and Y that is not a causal relationship. To see why this is the case, let's look at another extreme example. So suppose we have this DAG. We have A, Y, and an L pointing to both A and Y. We have this backdoor path. Okay, so if we look at this DAG, we know that A is not a cause of Y. There is no causal relationship between A and Y, right? They are just caused both by a third variable. However, if we do not conditional on L, then it is likely that A and Y will be correlated due to the existence of L and these two arrows. We have seen examples from the previous slides. Now, if we conditional on L, we know from this fork structure, if we conditional on this node, then A and Y will be independent conditionally. And therefore, if we conditional on L, we removed the spurious correlation. So that's why in assessing causal effect, we want to block backdoor paths from A to Y. These are all intuitive arguments which will lead up to a rigorous statement of what variables lead to conditional ignorability. Any questions for the backdoor paths definition? Okay.
Wait, can you go back to the one before, slide before?
This one or the one before that?
No, the one before that. Yeah. So if there was a variable, let's say W, that was use terminology, hopefully fork. I think it's fork. It goes to Z and Y.
So if there is a W that goes to Y and goes to Z, you're saying?
Yeah.
Mm-hmm.
So that's a problem, I think, when you're trying to assess the causal effect.
Okay,
But is that a backdoor path?
That's a good question. That is not a backdoor path. Let me see. Well, I can answer that right now, but I'll think about it and answer you afterwards.
Okay, thanks.
Yeah, thanks. So, okay, but just so that everyone is on the same page, Roy's question is kind of ahead of what we're talking about right now, but if we have also this variable W and arrows pointing to Z and Y, how do we, essentially, what are the variables we need to have conditional ignorability? And as we will see shortly, we will discuss a way to determine this, but but we'll see. There might be some issues. Okay, but anyway, let's move on. Okay, so we talked about front door paths and back door paths. And I just want to mention that these two types do not exhaust all possible paths from A to Y. And in particular, this would be an example that is neither a front door path nor a back door path. Actually, this almost is the example that Roy gives if we have an arrow from L to Y. But anyway, so for this situation, this is not a front door path or a back door path. It's not a front door path because it's not directed. We have a reverse arrow over here. It's not a back door path because it starts with from A to L, not from an arrow inside into A. So do we want to block this type of paths, or there might be other situations as well? We can use the backdoor criterion to determine. So let's see. So now we're ready to discuss the backdoor criterion. Okay, so what is a backdoor criterion? We have talked about what is a backdoor path, and we have talked about what is blocking a path. Because backdoor path is still a type of path, so we can still talk about blocking this particular type of path. Okay, so a set of variables x satisfies the backdoor criterion relative to A and Y treatment in the outcome if both of the following hold. One is that x blocks every backdoor path between A and Y. And the second is that no node in X is a descendant of A. We'll see examples and intuitions for this criterion shortly. But first, let's give the results that we've been waiting for. And this is that. So if X satisfies the backdoor criterion, then we have conditional ignorability. Okay, so the proof is given by Pearl and in 1995, but it's not very easy to read. Another proof is given by this paper. So if you're interested, I would encourage you to read this paper. Okay, and so this result gives us a connection between the potential outcomes and the causal DAG. So we have the potential outcomes here, and the backdoor paths and the backdoor criteria. These are all from the causal DAG's language. So therefore, this result provides a connection or a bridge between these two frameworks or systems. Okay, so now let's look at a few examples and see when the backdoor paths, backdoor criterion is satisfied. Okay, so this is our first example. These are the confounding examples that we have seen both on last lecture as well as the first time when we set out to discuss observational studies. But now we're ready to discuss them in more precision. Okay, so the question is, does working as a firefighter increase the risk of death? So here we have A as a firefighter, working as a firefighter, Y is death, and L is being physically fit. And this was the causal DAG that we were imposing for this problem. So now, okay, the question is, does L satisfy the backdoor criterion? Let's see. So there is one backdoor path from A to Y going over here. So because this is a fork structure, L blocks the only backdoor path. And also, remember there's another restriction on the backdoor criterion, right? Another part of the criterion is that L must not contain any descendants of A. And therefore, this holds as well because the only descendant of A is Y. So in this case, L satisfies the backdoor criterion. Okay, this is a second example. So the question is, does taking aspirin cause stroke? A is taking aspirin, Y is stroke, and L is some condition prior to prescription. So the doctor uses the information of L to prescribe the treatment. Okay, now let's suppose we have a common cause for L and Y. Maybe some underlying disease that affects both stroke and also the condition that's used to do the prescription. So now we can also ask the question, for example, does L satisfy the backdoor criterion? So again, to check the two parts of the criterion, the first part is, does it block every backdoor path? Here we have only one backdoor path here highlighted, and this is a chain structure here, so L blocks the backdoor path. The second part of criterion, L must not contain descendants of A. It's not. So therefore, L satisfies the backdoor criterion. Now, you can also easily check that U or L and U, they also satisfy the backdoor criterion. Any questions?
What would be the advantage of adjusting for both of them as opposed to one of them?
Good
I was
question.
wondering if maybe you had a good answer.
Yeah.
For that.
I don't know. I don't know the answer.
Yeah, I think
I
it's
don't know the answer.
situationally dependent.
Yeah. Very likely. Yeah, depends on the data and the actual model that you're using, I suspect. Yeah, but in here, in terms of conditional ignorability, doesn't matter.
Yeah.
Thanks. Okay, example number 3. We have a slightly different causal structure, causal DAG here. So does exercise reduce the risk of death? A is doing regular exercise, Y is death, and L is cigarette smoking. We're assuming that smoking and regular exercise, they don't have causal relationship with each other, but there are some other factor that affects both, right? This personality and social factors that affects both whether you smoke or not and how much exercise you do. So in this case, let's see, does L satisfy the backdoor criterion? Again, two parts of the backdoor criterion. First is, does it block all backdoor paths? We have a single backdoor path over here, and it blocks the backdoor path because this is a chain structure and L is the middle. The second part, L mustn't contain descendants of A. Here, A only have a single descendant, so and L is not does not contain Y, so that's okay. Therefore, L satisfies the backdoor criterion. And you can also check that in this example, the U or L and U also satisfy the backdoor criterion. Okay, so now I would like us to do another example, do another exercise. So let's look at this causal graph and please answer the following questions. I'll give you 4 to 5 minutes to work on it, then we'll discuss. But if anyone has any questions on previous slides, please speak up now. Okay. I'll have to interrupt you now. It's unfortunate that I can't see anyone's screen, so I don't know where you are. But let's see. Let's see how do we answer this question over here. So the first question is list all the backdoor paths from A to Y. So what do we have? We have, so a backdoor path would start with an arrow going inside of A, right? So we trace back with this arrow, then anything that connects from this to Y is a backdoor path. So this is one backdoor path. And this is another backdoor path. So in other words, the backdoor paths are A, Z, V, Y, and A, W, Z, V, Y. So these are the two backdoor paths. Any questions for this? Okay, so now the next question is, does Z satisfy the backdoor criterion? Can someone tell me yes or no? Your answer? Or I guess we can do this this polling thing again. Oh,
I think it's no.
okay. Yes, go ahead. And why is that?
Oh, because Z does not block the red one, I think.
Okay, Z does not block the red one. So in other words, you're saying that if we conditional on Z over here, this is the red path. If we conditional on Z, then this path is not blocked.
Yeah.
Why is that?
I think because Z, basically V, W, and Z form a collider, and Z is in that set, so.
Okay, thank you. Yes, that's very good. Because we have a collider structure, in order to block this path, we cannot conditional on Z. Or at least we cannot just conditional on Z. Good. So, and therefore the answer to this is no. Now, for the next questions, these are I guess more straightforward. So I'll just go through them. So does V satisfy the backdoor criterion? Let's see. So we have a V over here and we have a V over here. If we block V, then or if we conditional on V, it blocks both paths because these are not colliders. These are chains or forks. So that's good. Now the second question is, does V and Z? So if we conditional on both of these, of course it blocks this path. And if we, on the right, we conditional on both V and Z, this is a situation that we have seen before. Although we have a collider, but because we are blocking this entire path by this other variable in a chain or a fork, so it doesn't matter if you're also conditioning on the collider or not, because the information flow is blocked by this V here. Although conditional on Z introduces this spurious correlation between these two, but it doesn't matter since the information is still blocked in V. Okay, so the answer for that is yes as well. Then the third one is does W and Z, and similarly, the answer is yes. Because we conditional on Z over here, it blocks, and we conditional on W and Z, and the W part makes sure that this path is blocked. Any questions? Okay, that's very good. So you have seen that a lot of the tricky situations usually involve colliders. And here I had a preparation slide, but you have done a good job. So there is no need for this one. Okay, so finally, I would like to, Oh, and by the way, I want to mention that okay. So after class, if you wasn't have enough time to finish all the exercises in class, I would encourage you to try to do that after class. And I will post the correct answers to all of these questions, both from this lecture note and the previous lecture note on the discussion forum. Okay, so, well, we really don't really have the time to go through this. It's 1 minute before class is over. So I'll leave it there and I'll just remind you what we have learned today. The two most important things, I'd say. One is deseparation and the notion of collider and how it plays a special role in terms of conditional independence. Actually, it induces conditional dependence. The second one is backdoor criterion, and that implies conditional ignorability. So we have seen some examples, and next lecture we will explain a little bit more why backdoor criteria implies conditional ignorability, and we'll see how do we define confounder and how do we test for a causal DAG. Right now we are always saying that the causal DAG is taken as granted, but how do we construct one? How do we test whether a particular causal DAG is correct or not? We'll see these topics next time. So if you have questions, feel free to hang around. Otherwise, I'll see you next week. Thank you, everybody.
Thank you.
Thank you.
Thank you.
Thank you.